Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3, Iterations in Vectors, Part 5. We're still in vectors. This time we're looking at distance from a point to a line. Remember, we're not dealing with two-dimensional, we're dealing with three-dimensional lines. So what we learned previously in the previous video in Part 4 was how to make a vector equation of a line where you have r equals, and you have a point that's on the line as your starting place, and then you have a direction on how to continue on the line, and you also have a parameter that then allows you to multiply that direction or take a fraction of the direction or even a negative of the direction so that you can move from your starting point anywhere along the line that you want to. So this is how we set up the vector equation of the line. So what we're doing now is then bringing this into the application of how to find the distance from some other point to the line itself. Now, got a lot of stuff written on the board, so follow carefully as we work through it so that you know what sequence to go in. There are several ways that you can solve these. If you look at a mark scheme, they'll give you like 3 or 4 different options of ways of solving this type of problem. There are 2 reasons why I will follow this particular method. One, it's the one that I remember, and 2, I like it because it reviews a lot of the things that we've already covered in vectors. So it doesn't take information outside of what we've already learned. So I'll show you 2 examples using this method. The third example is a little bit different. The question isn't actually looking for the distance between the point and the line. It has a different question to it. So on the third example, I will cover a different method that you could use in these first 2 examples if you want to. Okay, so let's get started. Here we have our line. And basically, the only thing that we know about our line is one location, this point 425. So I'm just going to call it A, point A. And we also have a point that's not on the line, so I'm calling it P, point P. And it is given 3, -2, and 1. Notice they gave it in component form. They actually gave the equation of the line in component form first. So actually, before we get started, let you look at the question itself here. So it says the point P has the position vector 3i minus 2j plus k. The line L has the equation r equals 4i plus 2j plus 5k plus mu times I plus 2j plus 3k. So here you can see the point as well as the line are in component form. Find the length of the perpendicular from point P to L, giving your answer correct to 3 significant figures. Okay, so it's a distance from the point to the line, and it's perpendicular distance, meaning it's the shortest distance possible. It's not just a distance to anywhere. Perpendicular distance is your shortest distance possible. So it's looking for the distance right here. That's what it's looking for. So in this particular method, we're going to work our way around kind of in a circle here. So we know point P, we know point A. So the first thing that we're going to do is we're going to find this here. And first we'll find the direction, how to get there. And instead of P to A, and I'll explain a little why, I'm going to do A to P instead of P to A. So A to P, doesn't really matter which direction you go, but you'll see why in a minute, why I prefer to go A to P. So if we go from A to P, remember that means P minus A, P minus A. So here's P, 3 minus, or here's our 3, here's our A. So 3 minus 4 is a -1. -2 minus 2 is a -4. 1 minus 5 is a -4. Okay, so from A to P, it's -1, -4, and -4. Now, don't worry about the black part yet. So that gives us this direction. Okay, that's direction. Now we want to do the magnitude of that. So here's the magnitude of that. Square root of -1 squared plus -4 squared plus -4 squared gives us square root of 1 plus 16, which is the square root of 33. So here we have now one of our 3 sides. Don't forget this is perpendicular. So what we're doing is we're working our way around this right triangle. So we started from the known point going to the known point on the line, and we had to first get the direction and then its length. Now in here we have an angle. So if we do cosine of the angle, now why cosine? Because it's in our dot product. The only trig function that we've worked with respect to vectors is the dot product formula, which has the cosine theta in it. So it doesn't mean that you can't use other trigonometric functions with vectors, but as far as the new features that we've learned in vectors, we have learned specifically about cosine theta. So cosine theta is the adjacent, which would be A to N, and it's the length, that's why it's magnitude, divided by the hypotenuse, so magnitude of A to P. That's why I wanted to go from A to P, because when you're working with an angle, you want to be starting from the vertex, so A to N and divided by A to P. Then we want to find AN. So if we solve for AN equals AP times cosine theta. Well, this is very interesting because this is very similar to the right-hand side of the dot product, the scalar product. So the right-hand side has a magnitude and it has cosine theta, and it also has another magnitude in there. Well, if we want to put that magnitude in there without changing the value, we just multiply it by 1. So if we have a magnitude of 1, now we have the AP magnitude, the magnitude of 1, and we have cosine theta. So this is exactly like the right-hand side of the dot product formula. So if it's equal to the right-hand side of the dot product formula, then it's also equal to the left-hand side. And the left-hand side would be the direction of AP times the direction of 1. Well, what's the direction of 1? The direction of 1 would be the unit vector direction. So what we have is direction AP, that's going this way, and direction of the unit vector, which is this way. Now AP goes all the way from A to P. Maybe I should put it more like this, all the way from A to P, whereas the unit vector goes in the direction that we want to go, but only one unit, right? Because it's a unit vector. Also remember that your unit vector formula is the direction of the vector divided by the magnitude of the vector. Okay, so what we need to do is we need to get the direction of the vector, that is, it's in the direction of our line, so that's our 1, 2, 3, and we need to divide it by the magnitude of that. So the magnitude of our direction is the square root of 1 squared plus 2 squared plus 3 squared. So that's the direction of our line. That's the direction we want to go. And we end up with square root of 1 plus 4 plus 9, which is the square root of 14. So to get the unit, this unit vector, we need to do the vector divided by its magnitude. So if we take 1, 2, 3 and divide it by its magnitude, we get 1 over root 14, 2 over root 14, and 3 over root 14. So take the direction, divide it by its magnitude, and this is our unit vector. If you wanted to double check that, you could do the distance formula with this. In other words, you would square each of these just like you did down here. You would get 1 over 14 plus 4 over 14 plus 9 over 14, and you get 14 over 14, which is 1. That's the length of a unit vector. Okay, so if you really wanted to double check, you could. Now we want to do the dot product. Why the dot product? Because this is the left-hand side of the dot product formula. If AN equals the right-hand side of the dot product formula, then AN also equals the left-hand side of the dot product formula. So we don't actually have to know what the angle is because we're replacing the right-hand side with the left-hand side of the formula. So all we need to do is the dot product of direction AP. We already did that, the -1, -4, -4, with the direction of our unit vector, which is 1 over root 14, 2 over root 14, 3 over root 14. So when we dot product this, we get a -1 over root 14, minus 8 over root 14, minus 12 over root 14, which comes out to a -21 over root 14. Now, you don't need to worry about the negative sign. It doesn't really affect what we're doing. What AN is a length, and obviously lengths can't be negative. So this is really a length of 21 over root 14. Okay, so now we have two sides of a right triangle. Now all we have to do is the Pythagorean theorem. So the Pythagorean theorem is, your a squared plus b squared equals c squared. This is the hypotenuse, so it goes on the side by itself. So 21 over root 14 squared plus p to n or n to p, it doesn't matter which way you go because it's length, squared equals root 33 squared, which is 33 equals 441 over 14 because the square cancels the square root, plus pn squared. So pn squared equals 3/2. When you subtract that to the other side, square root both sides, it says take the answer to 3 significant figures. So the distance from P to N is 1.22. Okay, so just to review quickly before we move to the second example, you start with P and you're going to work your way around. We want to get around to this distance right here. So you start with your known, you figure out the direction to the known point on the line. It's this. Then you find its magnitude because direction only tells you how to get there. It doesn't tell you the length. So you need to do magnitude to get the length. Then we use the angle. Now you don't necessarily have to derive this out every time. You actually should be able to jump right down here to this part right here. Okay, I'm going to put a little asterisk on it. When you get over here, you don't have to start with cosine theta. If you forget, you can start with cosine theta and then you can derive it and it should come back to your memory. But all you need to know is that you take the direction of AP and with the dot product of the direction of the unit vector, meaning you need to take the direction and divide it by its magnitude because that's the formula for unit vector. The vector divided by its magnitude. So 1, 2, 3 is the direction of the vector. and then you divide it by its magnitude, and you do the dot product with your AP, which was this here. So that gave you the length, and now you just have to do the Pythagorean theorem, which you should remember that from junior high school. Okay, so that's how we get that. Let's go through basically the same thing, but with a different example. Okay, let's look at our second example here. Says the line L has equation R equals I plus 2j plus 3k plus mu times 2i minus j minus 2k. The point P has a position vector 4i plus 2j minus 3k. Find the length of the perpendicular from P to L. So again, we're finding the distance from a point to our three-dimensional line in vector form. So let's go back to the board here and work our way through it. So here is our equation of the line and our point, but I've changed it to column vector form. Again, I've explained in the past, I like column vector form better because it's easier to use mathematically than the component form. So what we want to find is we want to find this length here from P to N. Now, I don't think I mentioned it in the previous example. The reason why I call this N is because it's perpendicular and N stands for normal. Normal means perpendicular. So that's why I use the letter N. The problem already called this point P. So I just call this A over here. It doesn't really matter what letter you use, just keep track of which one's which. And so again, we're going to work our way around this. And remember, this is perpendicular. So we want to create a right triangle. So we're going to start with this side over here. And we're going to do, again, from A to P. Because like I said, later we're going to work with this vertex of this angle. So we want to start from the vertex. So we'll find AP. So AP is P minus A. AP is OP minus OA. So here's P and here is A. This one here is your point. So 4 minus 1 is 3. 2 minus 2 is 0. -3 minus 3 is a -6. So this is our direction A to P. That's how to get from A to P. But we want to find the length. So we need to take the magnitude of that, which is the square root of 3 squared plus a -6 squared, which is 9 plus 36, which is the square root of 45. So this right here is root 45. There's one of our lengths. Now we keep working our way around. Again, here is our angle next to the line. So if you did the cosine thing like we did in the previous example, like I said, you don't have to derive it every time. But at the end of that, you need to remember that the length of A to N is equal to the direction AP dot product with the direction of the unit vector. So the direction of A to P dot product with the unit vector in the direction of N. So to get our unit vector, we need to take our direction and divide it by its magnitude. So the magnitude would be the square root of 2 squared plus a -1 squared plus a -2 squared, which is the square root of 4 plus 1 plus 4, which is root 9, which is 3. So 3 is the magnitude of the direction. So we need to divide the direction by its magnitude to get the unit vector. So here's the unit vector, 2/3, -1/3, and -2/3. This is our unit vector. So direction AP dot product with the unit vector. So when we do that, this will equal 3 times 2 is 6/3 plus 0 plus 12/3, which is 2 plus 4, which is 6. So the length of this over here is 6. Length of AN. Now that we have 2 of the 3 sides, we can just use the Pythagorean theorem. So again, a squared plus b squared equals c squared. The 6 squared plus the pn squared equals the root 45 squared. Gives you 45 equals 36 plus pn squared. 9 equals pn squared. So the length of pn is the length 3. And that is our answer for the distance of the point to the line. It's 3 units away. Okay, so those first 2 examples both asked for the distance between the point and the line. Now I'm going to take you to another example that's very similar, but the question isn't actually asking for the distance, it's asking for something else. So for that example, I'm going to use a different method that you could still use with these 2 examples if you want to. When you go through it, if you feel like it's easier for you, you're welcome to try that method back on these 2 examples, see if you get the same answer. Then you can look at the 2 methods and decide which one works best for you. So let me set up for that one. Okay, here is our last example for this video. And let's take a look at it. And you'll see how it's a little different from the others. Although there's a lot of similarities. It says relative to the origin, the point A has a position given by OA equals I plus 2j plus 4k. The line L has the equation R equals 9i minus j plus 8k plus mu times 3i minus j plus 2k. So they give you a point in the line just like before. However, this time it says find the position vector of the foot of the perpendicular from A to L. So the foot of the perpendicular is that letter N, that normal spot that I put on the previous examples. The foot is where the perpendicular touches the line, and hence find the position vector of the reflection of A in L. So it's looking for 2 position vectors. It's not looking for lengths. And one of the position vectors is actually a reflection. So let's go back. Again, there's a lot of similarities. You have a line and you have a point. This time they call the point A instead of P. So this is A, so I just called this one P instead. It's the point on the line. And the foot of the perpendicular is point N. That's the foot. It wants the position vector of what I've labeled N because it's normal or perpendicular. So it wants that position vector. And it wants the reflection of A across the line. So the reflection just means same distance, but on the other side. So I just called it A prime. This is our reflection. Okay, so we're looking for those 2. So because it's a little bit different, I'm going to use this opportunity to show you another method that you could also use in the previous 2 examples. So what this method does is it looks at it as vector addition. I want to get from A to N. So A to N equals A to P and then P to N. So it's in a sum of 2 vectors. A to P plus P to N will give me A to N. So A to N equals A to P plus P to N. So A to P is P minus A. P minus A. 9 minus 1 is 8. -1 minus 2 is -3. And 8 minus 4 is 4. So from A to P, the direction from A to P is 8 minus 3 plus 4. Or 4, 8, -3, and 4. And then how to get from P to N? Well, we were already given that up here. Our starting point is P, and then to get to any other point on the line from our starting point, here is the directions. So all we have to do is add on to that the mu that is some factor times the direction along this line, which is 3, -1, 2. Now, we don't know that factor yet, but we know that once you get from A to P, you now need to go in the direction of the line some multiple of the direction to arrive at N. So if we put that together into a column vector, we get 8 plus 3 mu and -3 minus mu and 4 plus 2 mu. And because it's perpendicular, we can take this direction that is now going from A to N, even though it's by way of vector addition, it's still from A to N, and that is perpendicular to the direction of the line. So here's the direction of A to N, here's the direction of the line. Since they're perpendicular, it means the dot product should equal 0, because cosine of a 90 degree is 0, and it wipes out the right-hand side of the dot product formula. So if we dot product these, we get 3 times this, which is 24 plus 9 mu. Multiply these, we get plus 3 plus mu. Multiply these, we get plus 8 plus 4 mu. Set it equal to 0. Gives us a total of 9, 10, 14 mu. 24, 27 plus 8 is 35 equals 0. Move the 35 to the other side, divide by 14, and it reduces the value of mu is a -5/2. So what that means is this is the value of mu that causes this to be perpendicular. It also gives us the value of mu to allow us to find N. One of the things we need to find is the position vector of N. Notice it's not asking for this distance. It's only asking for the position vector. So if we start from this point here, and if we know the multiplier here, we can calculate where that point is at. So we plug in the -5/2, so we get 9 plus 3 times the -5/2, -1 plus -1 times the -5/2, and 8 plus 2 times the -5/2. So we end up with our N. This is our location of N is at 3/2, 3/2, and 3. So what I've done over here is I've put in A, which is down here, 1, 2, and 4, and I've put in N, 3/2, 3/2, and 3. These are the position vectors, and the reflection of A to the other side, which I put as A prime, is the same distance, but you don't actually have to calculate the magnitude. All you need to do is make sure your X, Y, and Z move the same number of units. So if we start with A, notice these are in halves. So if we change 1 into halves, it's 2/2. And if we change 2 into halves, it's 4/2. So we go from 2/2 to N, which is 3/2, means it added a half. So if we add half again, we get 4/2. Now we're going down a half. 4/2 to 3/2 is -1/2. So if we -1/2 again, we get 2/2. And here we have whole numbers. 4 to 3 is -1. If we -1 again, we get to 2. So our position vector for A is now 2i. We'll put it in component form because the original question gave it in component form. 2i plus j plus 2k. So there is our reflection, and our N is 3/2 I plus 3/2 j plus 3k. That is the position vector for the foot of the perpendicular. So the foot of the perpendicular is this one, and the reflection is this one. So that's how you solve this problem. I used a different method because we weren't required to find distance. If you wanted to find this distance, once you found position N here, all you have to do is go A to N or N to A, doesn't matter. So if you go A to N, it's N minus A. Find the direction there, which actually we already found right here. We found the direction of A to N. So you could take this -5/2 here and probably plug it in here. Either way, it would probably work. You found the direction from A to N. Plug in your -5/2 for the mu, get your direction, and then find the magnitude of this. That would be the length. Or if you came down to here, take N minus A or A minus N and find the magnitude of that. Either way, it will give you distance. We didn't need it for this problem, so that's why I thought I would just introduce you to a new method. You can compare the two, see which one you like better, and the important thing is that you can remember it and that you understand how to use it. So there's two methods on how to find the distance from point to line, although in this case we didn't actually do distance, we did location of the foot of the perpendicular and also the reflection. So I hope that helps. This is the end of the vector content. Remember that all of it from what used to be part in P1 and part in P3 now is all together in Pure Maths 3. So I hope that you can be successful at this question type. Thank you for joining me in the Zoom room and hope to see you again next time.